Hello, everybody. Thank you for attending this webinar on forecasting. We're going to talk initially about the integrated solution where the forecasting is embedded, and then we present the forecasting part, and we will have a live demo. So let me start the presentation. So my name is Jesse Tay, and my colleague Michael Johnson will be presenting. I'll do the introduction with the PowerPoint such that you focus yourself on what the forecasting is, what the AQMIS is, and Mr. Michael Johnson will then do the live hands-on. This is an overview of the benefits of integrating information, and I will see why we need the forecasting and the benefits. So forecasting is very important for public protection. So that's why governments will show AQIs, for example. But we need AQIs for 24 hours ahead so people can plan. There are locations that we only need protection for ozone. I say only as comparing to if you have dust storms. So as an example, in the Middle East, there are severe dust storms. We can forecast 24 hours ahead, and then people need to close operations because then equipment will be damaged. So in addition to ozone, we need to protect against other events. It's necessary for compliance. We will see that there are plants that if they operate certain ways, they will exceed the maximum threshold and concentrations for a number of pollutants, and they need to comply. So we put them into compliance. And then human exposure, and it's important even for planning hospital staffing. Let's say that an event will occur on the city high ozone levels, as an example. More people will show up with asthma attacks or some other respiratory problems in the hospital, and we can then support these type of activities. So we're going to see the benefits, have a brief overview of the system that integrates all the parts we need for the forecasting, and Mr. Michael Johnson will do a hands-on and show that to you. Then we have the question and answer. So the benefit, the main ones are because regulatory agencies, the annual budgets are always being cut. It's interesting that everybody talks about the environment. First thing they cut when they get in power, environment. Consultants become preferred when they run the system. Lake's software is not an environmental consulting company. So when we team up with consulting companies, environmental engineering consulting companies, and they then become a preferred on all the subsequent years. We have in Canada companies that are preferred for 10, 15 years, and they're still running our codes in the client and doing all the field work for that. And then facilities have an enormous cost reduction and less red tape. And I will talk about some of the cost reductions that I mean in a few slides ahead. So the system is fully integrated, and this is important to fully integrate because the benefits are incredible. So the system will do emissions inventory. So we'll do for static emissions inventory or dynamic. What do I mean by static? Static is the one you do every year to report. The dynamic is we know what the emissions are every minute in a facility. So let's say it's a oil refinery. So we know how much is being emitted of benzene, for example. So we can dynamically tell what the operation needs to be. Let's say it's SO2. So if we have the estimate of what the emissions are with the current fuel and production levels. We can then run dispersion models and identify that we have a problem. We can also estimate what the emissions will be, how we need to change the emissions, and provide that to the facility such that the operator can change, for example, in an oil refinery, they can change from sour gas burning to sweet gas. It's more expensive, but then they will comply if the SO2 will exceed regulatory limits, such that when it hits an ambient air monitor, a AQMIS, then it will be in compliance. It will not be exceeding and giving a higher concentrations than allowed. So let me stretch this slide. And then we can conduct human health risk assessments, can do the permitting, every year issue the regulatory things, audits inside the company and enforcement by regulatory agencies. So there's enormous benefit by integrating. This is an example of the dashboards. So at any moment, a regulator or an operator can know what the concentration is or what they will be. So the red line indicates that at this moment, there will be an exceedance. Concentration will be above the regulatory limit. So we can do that. Furthermore, we can add more value to monitor stations because we can have the monitor station can forecast what it will measure, and we can establish pollution roses such that we know where most of the pollution are. And we had cases with pollution roses where an oil refinery was here being investigated by the regulatory agency, and just not doing dispersion modeling, just using a monitor station, using the pollution rose, which is similar to the wind rose. We knew that the pollution, the impacts were happening coming from here, and there were a petrochemical plant here, causing all the problems on this monitor station. So we add more value to the already value that we get out of a monitor station. We have lots of clients, ones that we want to mention, for example, running this. All the nuclear reactors in Korea, they use our system. We have a system running Kuwait. We have oil refineries. We have drilling operations. Let me explain that. Here, smelting. So we have lots of clients on smelting, pulp and paper, etc. So we have an oil refinery as an example that they were sued and lost the cause because they were impacting a tribal land, and they couldn't operate. So the only way to operate was to using our system. They can then plan how they operate, what they burn, and how they burn, and when they burn, such that they are always in compliance. And now they can fully operate, and everybody is protected. Mining operations for dust and smelting operations. Let's say you get nickel, and then you need to smelt that and remove. You got nickel sulfide. You're going to burn that and generate SO2, massive amounts of SO2. That SO2 will be cleaned out of the plumes getting out of the stack in an acid plant, but they still emit because the acid plant will be incapable of filtering out 100%. So they will have some impact. and then we can forecast how to change the operation ahead of time, so they have enough lead information to change the operation, such that when the moment arrives, the emissions are below what causes an exceedance. So they can plan operation, and they can see even real time what's happening, and we compare all the time what the monitor is doing and what we think it should be doing. So the model has automatic evaluation, so we know how well we're doing. We've been doing this extensively for more than 15 years, and we have the best experience in the world in this field. Drilling for oil and gas, sometimes you drill and you know you're gonna get a massive amount of H2S. H2S, we know it's a very stinky gas, but if it is above certain concentrations, it will then kill people. It can kill an entire city, village. So we can forecast when to drill, because they will need to burn that. But until that happens, an accident happens and they have gas coming out, it's a disaster. So we can plan for that. So let me go here. We can do different studies with AQMIS, such that segregating from a monitor, you do not know if concentrations are coming, what is causing that concentration, the point source, area, volumes, commercial, on-road, non-road, what is causing it? So we can segregate the information using AQMIS. Have high-level information at jurisdictional level, on-road, with dashboards and all the information, greenhouse gases, extensive use of mapping, conduct then human health risk assessment, various types, acute or chronic, long-term, permitting, all together, and then the reports, greenhouse gases, and now the forecast. So this is what you came to watch, and let me talk about a little bit about it. We can do forecasting using phenomenological, intuitive, and we have been in many facilities where the operator has rules and has seen what happened in the past when certain things happened. So it's almost on a gut feeling, as experience, and then goes on the gut feeling. And this is not accurate. This what caused a certain site was exceeding smelting facility, and they would have to stop the entire operation. Imagine 200 meters to 300 meters of molten, red hot, initially molten and then red hot metals that you have to stop. That will all solidify on top of the equipment. So that's $10 million per stoppage. Maintenance, loss of production, change of parts of equipment, it's a mess. And some of the companies we went and helped were having it 4 times a year. So that would be like $40 million in stoppage, necessary stoppages. When we implemented our system, and this using the phenomenological, the empirical, the intuitive. And when we entered, we resolved the problem and reduced from 4 to 0, no more exceedances. So, and there are many ways to do it. Some people use statistical, use regression equations. Basically, you see here, you do a regression. It's not the best thing to do. You can use neural networks. Today is well developed, and in certain cases, it's the thing to do. I'll show you when. And also using dispersion modeling, CalPath view, SkiPath view, Austal, etc. we use those. So many, the emissions calculations are mandatory. We must do it because how can we forecast what's happening? For forecasting, we need to do the dynamic emissions inventory, and we can do that with over 11,000 different processes that emit to the atmosphere. We even do calculations throwing drones and using AI to estimate the vehicle density on the roads. Because you say, oh, I can go in the Department of Transportation, get the vehicle distribution. So get the vehicle classes. But you do not know the spacing between the vehicles and the density. It's something that we can do very precisely, throw the drones and use AI that we developed. I supervise a PhD student on this. So we developed this and we know what the vehicle is, what vehicle type, spacing, the speed. So we can do forecasting for roads as well. So we run the dispersion models after we have the emissions inventory. And we have the one we don't use is AirMod. Even for flat terrain, it's not the best option for real time. AirMod is very good using it the way it is for permitting because it runs in a stochastic way. I can explain that another time or questions if you will. But for real time, we need to use from number 2 to number 8, ideally 2, 3, and 4. And one of the reasons is with SkiCam, we can have the chemistry of CMAC right here, photochemistry, and we can trace back to the source. This is what we are doing real time in Qatar for the World Cup. So World Cup, we need to forecast what's going to happen with the industrial activities and shut down those or reduce the production of those there impacting the air quality for the entire country. So we can do real time for the entire Qatar. Ambient monitoring, what we see is just this. And we do also the pollution rules. This is SO2 pollution rules. This is exactly the case we mentioned where the impact, a refinery was here and the petrochemical was here. It was the impacting the most was the petrochemical. So we also use neural net. I have taught courses in the PhD level on neural nets, and I developed here a system that can forecast. So we have, let's say we need to forecast ozone, and I do not have the emissions inventory because it's expensive, takes time running, doing the emissions inventory, and then running photochemical models all the time. It is expensive. It gives good results, no doubt, but it is expensive. So I developed one that I get the monitor data, and then I can forecast as good or almost as good, but as good as photochemical models, just using and forecasting quality, just using neural nets. And this is an example. We in California, they told us you could not forecast Schefter because we're having ozone problems. And I know the photochemical model, why it's not as accurate there. There is a specific reason. I can answer in the questions if you want. And we were doing outstanding. Look, we're forecasting 24 hours ahead. Look at that. This is crazy good. And they said, okay, now you cannot do Tranquility in Fresno. We're doing even better. There it's even easier to forecast. Look at forecast here 24 hours ahead. Can also use it either the modeling using running WRF to forecast the wind fields, run CalPAF or SkiCam to forecast ozone, or CalPAF cannot forecast ozone, but SkiCam can, but you can forecast other impacts, SO2 with CalPAF, and it gives good results, as good as the SkiCam. And you can also forecast air quality using neural nets or the models. So we forecast air quality, and we're the first one doing this for air quality, commercial air quality, for forecasting using neural nets. And we are, as far as I know, the only doing very large facilities using models with the accuracy that we have, nobody can match. So far, nobody can match. So as an example of the forecast, so this is an example we ran in this plant does not exist. That's why I'm using it. It used to be a coal-fired power plant, and it's off. An impact over the city of Toronto, which was significant. And this is in Qatar, this one over here. This is an island with storage, and the impact, we forecast hour by hour what the impacts are, and our impacts in Qatar with ozone and so in the model, and we have validated against monitoring stations ozone, for example, and they match really well. We use models there. So I'm going to go to the live demo, and I'll pass them to my colleague, Mr. Michael Johnson.
Thank you, Jesse. That was very informative and a great introduction. So here I just wanted to spend a few minutes discussing the capabilities of the AQMIS RT solution and show a few of the key points that help operators and engineering staff be able to make the best decisions for air quality. So first off, we just want to note that you have across the top 4 status indicators that show the concentrations. So what we can see off-site, here we can see them on the map, and we can see them across the top. We can see if we have a forecast exceedance, so if we need to look at that page, we can click on that page. And we have the data quality status saying that the data that we have in hand is good, but we are having some difficulties with the data feed status at this point. So this is something for us to look at, because we need to know that if we aren't getting data from the outside correctly and in real time, we know that we are not seeing the best information. But for now, we just have the telemetry page, and we can see our AMS concentrations. So we can see kind of our modeled and predicted times and our fly time. So that is basically the time it takes for the plume to reach one of these particular stations here shown on the map. Now, what you can see is that because the wind is not blowing towards any of our stations and it's blowing away from the city, we can see that we don't have any modeled or measured values that we would be looking at it at the current time. We can also see on our page our current net conditions, so we can see the wind speed, wind direction, temperature, so forth. And we can see if there were source contributions, we would see those as well. On an advanced telemetry page, again, for non-operators who want to look at different aspects, we can see the concentration values, the met station, but we can also do movement in and out. We allow for this simply to allow that advanced operators would be able to look and zoom in. However, these are folks who are not responsible for operating the plant, and so they don't need to be seeing the plant at a glance because they may be doing other things and they don't want to be lost. So here at this point, we can see here again our plume, and we can see the calculated fly times for the plume. So this is just another way for more deeper investigations to take place, and we can see the plumes. We can see also at the bottom the emission rates. So if we're seeing something unusual, we can see if there's been an upset here in the process, and we can look at different stacks and see how they're being emitted. So we can look at stack 3. We can see in our simulator here we have predictable stacks and values. So beyond these kind of dashboards that are used for operations, we can look at different kinds of real-time effects. So we can look at, for example, an animation, and we can see, for example, what we have seen over the last, say, 45 to 50 minutes. And so we can say, show the animation. And here you are able to see the plumes from different facilities and how it's progressing in real time. So this just allows you to see, okay, this is what we just saw. And so given the current conditions and maybe normal typical weather patterns, you would be able to predict and control your emissions as expected. Some other things you can do is you can look at AMS, and you can look at model versus measured. So you can look at different stations and see how well they're measuring. So obviously we have some elevation here at the end, and we have some otherwise we are matching quite well with the values. We can look at contributors, and we can see a pie chart. So if we need to control a particular source, we can see which one is giving the most impact off-site, and we can control those. We can look at things like the wind field, as Dr. Jesse explained, because we are using a model like CalPUF, and the multi-level wind. We can see that, for example, the wind is blowing north here at the ground level, but as we go higher up, because there's less friction, we can see that the wind is now progressing from the northwest to the southeast. So you can see this quite handily and readily. This just allows us to see, for example, if we have a very tall stack, we can see why the plume is going in a particular direction as opposed to lower level sources such as fugitives. Now, if we look again at our forecast, we can go ahead and see every 6 hours, we can see an update of various facilities and offsite monitoring points, and we can see what we're predicting as far as impact. So if we change no operations, we can see that we are headed to exceedances and breaches later in the morning, and then we can see that it calms down. But obviously now with this forecast, we can be more aware and we can modify the operations to do as we need. So if we wanted to see that graph, we could see here the two different peaks that we saw in the forecast, and then we can see that there's that elevated height at later in the day. And we can see these set points for the thresholds and the regulation, so we can try to smooth this out during our operations during the day. Lastly, I just wanted to close out, because I know we don't have a lot of time, we want to leave time for questions. We can see the animation forecasts. And so here again, we can see based on the next 6 to 12 hours, we can see how our plumes are going to evolve and how they're going to impact off-sites. And we'll be able to look at those values and see, you know, okay, we saw where we saw the hits and the high points, and we can say, oh, okay, so here at this hour and this time of the day, we know that we need to do a control or a curtailment in the operation in order to avoid an exceedance or a stoppage. Okay. A few other things we can do are run reports. We have lots of them. We can look at emission rates, meteorology, if we want to look at different things for the temperatures going forward. And we have also a way to set up and configure for a startup condition, so that if you are coming off a shutdown or you're going into a maintenance period, you can see when it is the opportune time to start or not start up, because there may be excess emissions during your startup scenario, and you want to be able to predict that. So let me go back and just show the forecast again and the animation and let that play out. And with that, I will hand it back to Dr. Jesse.
Thank you, Mike. This was really well presented. I will go back here on for the question. Thank you, Mike. That was well presented. I'll go here for the questions. Anybody have questions? Okay, I already got one here. Question is, why are wind at different heights? Our system can forecast the different wind speeds with different heights. As you go up in the atmosphere, the wind is faster. It is faster, and it also blows in different directions. So one of the things that was confusing the operators, and we then developed this system to show them, displaying what we were calculating, is that the operator was looking at the wind from the MET station blowing one direction, and we're showing the plume going in a different direction. And they thought our system was wrong. So we have to clarify that as you go up in the atmosphere, the wind is changing direction. and it is also faster. That's why the plumes were different. And we show that the wind, and now it's very clear for everybody. Somebody else took me on saying, if you have questions on why not use air mod, ask me during the questions, and somebody did. So the air mod is a good model to issue permits. We operated many hours, like say 5 years, hour by hour, and then it will give a good estimate of the maximum impacts. The thing with air mod is that it's a model that does not know what happened in the very previous hour. So if wind is blowing towards north, from the south to the north, and it shifts to blow from north to south, all the tonnage, all the mass in kilograms of SO2, as an example, that were blown in that direction, when the wind changes direction, it will forget about that SO2 from the previous hours that were emitted. And it will think the air coming is all clean, has no clue that there were any emissions before that hour. Now it's blowing from north to south. It has no clue. And it is very important to keep track every minute, every hour, where the pollutants went. So that's why we need to use a PAF model. So CalPAF is very good if you do not have chemical transformations. As example, if you have your impact is SO2 and it's within 10, 20 kilometers, then it's fine. If it is older, it is a good model. But if you have chemical transformation, then we must use SkiChem. Another question, which is what type of weather does the software accept? Local weather station, that's the question. All right, we use, in a lot of our sites, we use both local stations and satellite data. Should I say satellite data? Yeah. Remember that a MET station, it is a valuable instrument. What I'm going to say here, please don't think I'm saying it's not good. I'm just saying that it's a point of information in space. Beside that point, I have no more information. It also cannot forecast what will happen in the future. It just knows what's happening now and does not know anything else. So we use then a WRF model, extract data from satellites, and then adjust for the location, has information of topography, etc. It will produce information that is very good. And CalPAF can only, and SkiPAF can only operate well if we have these models operating, because it will not do well away from the station. So we use the station because that's real measurements and we know what's happening, and we adjust that with the WRF model. And then when we run, we have very good wind field. So we need to use, we can operate if it is tall stacks, we can operate using only WRF data. But if we have fugitives, we need the MET data, because the MET data then knows what's happening close to the ground, usually measured 5 meters above ground. I love when the stations are multi-level, but I never find them. Nobody uses it. But we will add a lot of useful information if it is multi-level. But at 5 meters, we're going to have, I'm sorry, we'll have it at 10 meters. We will have that information at 10 meters. And it would be nice to have at 1836, for example, because then I know how the wind is in that point, changing the speed and direction. So yes, we use for tall stacks was no information from the ground that not as important. If you have fugitive, the MET station local, very important. I'm wondering why WAR model is not a good model for the real-time prediction. Sorry, I reread that one. How much time can be forecasted? That's a very good question. Let me tell you the short and then how far. So a lot of facilities, they want us to forecast 15 minutes ahead, an hour ahead, and then hour by hour for 24 hours. Because the operators and people operating the plant need time to change how the plant is operating to a new mode of operation. I gave you an example, I will repeat. They need time to change from a sour gas to a sweet gas, and then they will abruptly reduce the emissions of SO2. Cleaning the gas costs money. So then you can operate, and people think, oh, refineries make a lot of money. You have to be careful with this statement. Per unit that is produced, let's say a liter of gasoline or gallons of gasoline, the profit is minimal. Why they make millions and millions? Because then they make millions and millions of gallons and liters of gasoline. But because the profit is, the margin is so thin, any mistake in the operation puts them in deficit per liter. And again, they make millions and millions of liters, and then they're going to have millions and millions in deficit in the red. So they need up to 24 hours. Now, beyond 24 hours, the models, WRF and any other forecasting model, they are very good at 24 hours. Now, the farther you go in the future, the less accurate it is. So we can do 48 hours, but we can also update that every hour. That 48 hours, I forecast 48 hours. Next hour, I forecast another 48 hours. So the hour I forecast is now 47 ahead and so on. So it's 48 hours, but the resolution reduces. People are asking about the system account for temperature inversion. Absolutely. It does, and it's if we don't do that, we're gonna miss most of the big impacts. Let's say it's flat terrain, just to simplify. Nighttime, we do not have convective cells. Convective cells in the atmosphere produce daytime, where the sun hits the ground, warms up the ground, and then the ground is warmer than the air, warms up the air, and then it creates convective cells. These convective cells start growing, so they're tiny when they start, obviously, and then they're getting more and more potent. And so convective cells start growing and going to, they can go in the summer, let's say no clouds, to a mile high. So no matter how tall your stack is, the convective cell will be higher than that. Now, nighttime, we don't have convective cells. So the inversion, or the mixing height, if you will, is shallow, very close to the ground. Let's say 30 meters, 40 meters. So the air will mix below there, but above, the plume will not hit the ground. The plume will go, and there is no mechanism or a strong mechanism to bring the plume to the ground. So that plume will travel very far without hitting the ground. So daytime comes, the convective cells start getting more potent. At some point, the mixing height, the inversion layer, will hit right where the plume is. And then it will bring the plume very fast down. That's called fumigation. So, or inversion breakup the moment it hits the plume. It's called the inversion breakup. And the term of bringing the plume down very fast is called fumigation. So we must forecast that very precisely, and we do that. Another question is, what is the maximum extent? Okay, when we have short distances of 10, 20 kilometers, CalPAF will do a very good job. Beyond that, then we start using ski cam. So CalPath will do a good job up to 200 kilometers, but very precisely it will do like 20, 30, 40 kilometers. SkiCam use SkiPath, which can do very good calculation to 2,000 kilometers. So in Qatar, we do 600 kilometers. And so we need to use SkiCam. We also need to use, because of the photochemical model that exists inside SkiCam, which is SkiPath plus the photochemistry, and it's the CMAC photochemistry right into the model, and CalPath doesn't have that. There's a question to explain the models. CalPath is a path model. It's used to be the only model accepted in the US for long-range transport, meaning beyond 50 kilometers. Doing dispersion models, you would have to use CalPath, but now it's at the same level as SkiCam, SkiPath, and SkiCam. So Austal is a model used in Germany, extensively used. In Germany, everybody does dispersion modeling, and every industry, and they apply dispersion modeling everywhere. Even for older, we basically everybody using, with only 2 exceptions, use our Austal view in Germany. So it's very well known and has a very good reputation. So Austal, it is a better model when we have urban environment, because then if you use CalPath or AirMod or SkiPath in urban environment, it will ignore the street channeling, air channeling through the streets, for example. So if I'm in downtown Manhattan with those tall buildings and I have the road, the streets, the avenues, the car emits CalPath, AirMod, and SkiPath will expand those pollutants through the buildings, and it's not what physically happened. Austal, it will hit the buildings and bounce the pollutants back inside the road. Yeah, so I think those were the questions. Do you have any additional questions? Okay, I'd like to thank all of you. If you have questions, please email aqmis@weblakes.com. We would be very happy to interact with you and clarify them. So on behalf of Lakes Environmental and my partner, Mr. Michael Johnson, I will wish you a wonderful rest of the week.